Hey everyone, in this video I'm going to show you how to calculate the instantaneous deceleration that an F1 car will experience at top speed. So imagine an F1 car on a straightaway, and right before it gets to the corner, the driver lifts off the throttle, and before he can press on the brake, the car experiences an instantaneous deceleration only from aerodynamic drag. That's what we're going to calculate here. So that's the goal. The steps that we'll be using are first to lay out the equation that we're going to use. The second step is to lay out some knowns and assumptions that we'll be using, and then the third is the solution. First step is the equation. You can see it written here, and this equation is the same as the one that I used in my how to calculate the top speed of a car, so if you have any doubts, go check out that video. And what this equation is saying is we have a certain amount of power available from the engine, and that's being used to overcome aerodynamic drag and to accelerate the car. And we're also going to be using the fact that power is equal to force times velocity. That was also sort of semi-derived in my other video, but you can just take it as it is. And so when the driver lifts off the throttle, we will have the engine power is equal to 0 watts or 0 horsepower. I use watts because that's what this equation is going to end up in terms of the units. So when the driver lifts off the throttle, there's no more power from the engine to the wheels. So we have 0 is equal to P aero drag plus P acceleration. So what are these two terms? P aero drag is down here. We're just using this equation here. So we have the F from the aero drag times the velocity. The force of drag can be written as this, 1/2 rho v squared CdA, I'll explain this on the next whiteboard, times the velocity here, and we're just going to multiply the velocity through, so we end up getting 1/2 rho v cubed now CdA. The power acceleration here we can rewrite as the force from acceleration times the velocity. This is the well-known F is equal to ma, assuming that we don't have a changing mass with time. So we can substitute in ma here, and we have P acceleration is equal to MAV, and taking this equation, setting this equal to 0, and bringing this to the other side, so we're just subtracting this from both sides, we end up getting that the P acceleration is equal to negative P aero drag. So the next step is just to substitute in this and this into this equation. So here I've rewritten that equation up here, P acceleration is equal to negative P aero drag. I'm just going to plug in those values from the previous whiteboard, and we get MAV is equal to negative 1/2 rho v cubed CdA, and I'm going to solve for A because we're trying to find that instantaneous acceleration or deceleration, and so I'm just going to divide both sides by MV. You'll note that one of the v's here cancels, so we end up having v squared on this side, and then we have the m in the denominator, so I can write it as A is equal to negative rho v squared CdA over 2m. And now here I'm going to define all the terms in the equation. A is the instantaneous acceleration. Because it'll end up being negative, that means that it ends up being a deceleration, but it's still technically an acceleration, is just a negative acceleration. And it's going to have units of meters per second squared. We can convert that to G's later on, because that's something that people are interested in. Rho is the air density that we're driving through in kilograms per meter cubed. V is the velocity, the instantaneous velocity, so we're going to be using the top speed of the car through a speed trap, and that's in meters per second, so we'll need to convert from kilometers per hour to meters per second. CD is the drag coefficient, and it's unitless. That's why this is empty. A is the frontal area, it's a characteristic area, and that'll be in meters squared. And then M is the mass of the vehicle plus the driver, and that'll be in kilograms. And I've noted here that C, D, and A might be sort of difficult to come by for certain types of cars, especially F1 cars, so I'll be combining this into a term CDA, so this is just the multiplication of the two, and that'll have units meters squared, you'll know, because we're multiplying a unitless number by one that has units of meters squared. And this is a number that I found from a blog post from a guy that quotes Peter Windsor about a typical CDA value for an F1 car. Let's move on to the knowns and the assumptions. I've rewritten the equation here. A is equal to negative rho v squared CdA over 2m. So we're going to need to assume some values for all of these in here so we can calculate A. The first one is that I'm using the Bahrain GP 2016, and that's because it's approximately at sea level, which comes into play here, where I'm assuming the density of air is equal to 1.225 kilograms per meter cubed, which is a standard error assumption, and the standard error assumption is at sea level, so I'm going to be using that. The third one is that the max speed that we're looking at is 335.5 kilometers per hour, or when you convert it is 93.19 meters per second, and this is on the FIA event and timing PDF that I found online, and this was for Bottas going through the speed trap and qualifying. The fourth one is that the CDA is approximately 1.3 meters squared, and that's from that blog / Peter Windsor's account of what a typical value for CDA is of a typical F1 car now, and so I'll link to that in here and then the video description. The fifth one is that the mass of the car is 722 kilograms. This is from the 2017 regulations, minimum for the driver and equipment and the car, but for no fuel, and you'll see that since the mass is in the denominator, that a lower mass will give us a higher deceleration. So I'm just doing this for when the car is almost empty. This is when you're going in qualifying, you want the fastest cars, you're going to have the least amount of mass that you can have. So we're doing this for no fuel. This is just the minimum mass that the car can be based off of the new 2017 regulations, even though this is for the 2016 stats. It doesn't really matter. You can plug in your own values. This is just a characteristic case. And then 6, this is not really an assumption, but that the acceleration due to gravity is 9.81 meters per second squared, and we'll be able to find the deceleration of the car in terms of G's using this. Now we can solve for the final acceleration. So we have the equation again rewritten. A is equal to negative rho v squared CdA over 2m. Let's plug in the values from the previous whiteboard. Rho is 1.225 kilograms per meter cubed. V is 93.19 meters per second squared. This has to be in meters per second. You'll note that all the units cancel out so that you do get an acceleration in meters per second squared. CdA we're doing as this single term, 1.3 meters squared. In the denominator we have the 2 times the mass of 722 kilograms. And when you plug all this in, you end up getting that the acceleration, the instantaneous acceleration right when the driver lifts at top speed, only due to aerodynamic drag, is negative 9.58 meters per second squared. We can find A, the acceleration or deceleration, in terms of G's by taking the one that we just calculated and dividing it by the acceleration due to gravity, and you'll note that it ends up being unitless, which is just the same as saying a certain amount of acceleration in G's. And so if we take that equation here, we have the negative 9.58 meters per second squared divided by 9.81 meters per second squared, and that gives us a final result of our acceleration is negative 0.976 G's, which is a deceleration of 0.976 G. So we're almost at 1 G of deceleration from this top speed, and that's pretty incredible for these kinds of cars. So this has been a video on how to calculate the instantaneous deceleration due to solely aerodynamic drag at a certain velocity. I chose to do it for the top speed just because I think that's the most interesting case, and I did an F1 car because I happen to like F1. So if you stayed this long, thanks for watching.